There's a story waiting to be told in these rocks, a story of past environments. The key to deciphering this story of past environments back in the Carboniferous 300 million years ago is to make detailed observations as we go up this succession. And that's what we're going to do in this video. And it's particularly easy to do this here because the rocks are dipping at about 45 degrees, so we very quickly go up the succession. We're only going to look at about 20 metres of sedimentary rock sandwiched between two limestones. I'm sitting on the basal limestone, and then we'll work our way up to a limestone about 20 metres above us. So the first thing then is to have a look at this limestone, and the best way to do that is to look down the direction of dip, and we can do that from over here. Well, this is the limestone. It has a very sharp base with the underlying lithology, more of that later, and it has a very sharp top, so there's going to be no difficulty working out the thickness. "65 centimetres. Now I know it's a limestone because I've already tested it with acid and it fizzes, but what about the lithology? It's no good just saying it's a limestone calcium carbonate. We do need to look at it more closely. So let's have a look at it with the hand lens. It still looks extremely fine grained. So most of it must be a carbonate mud. And what's the name for that? It's a micrite. So that's the predominant part of the rock, probably 80% or more is carbonate mud, micrite. But I can also see little fragments, little shell fragments, mostly crinoids. And it's possible to actually see them in places where they're weathered out, for instance, along here. So if it's got skeletal remains, crinoids plus micrite, the rock name is biomicrite. So it's a very low energy sort of condition that led to the formation of the limestone. Well, it isn't uniform throughout. Broadly, we can divide it into two. The lower part weathers to this rather rubbly appearance with little lenticular shaped bits sticking out. There's one here. In fact, this is probably a flattened burrow. It was once a cylinder, has now been squashed when it was compacted. And when we see it on bedding planes in fallen blocks, you can see some faint tubular structures. So clearly this rubbly appearance is due to biotubation, the mixing of the purer carbonate with less pure carbonate with some non-carbonate clay present. And then the top part, the upper 30 centimetres or so, is rather more massive, irregular layers separated by irregular parting planes. In some of the fallen blocks, we do actually see corals about in this position. So we've clearly got evidence with the crinoids and the corals that this was deposited in a marine environment. And there are other fossils present. On the top surface here, there are some wonderful examples of trace fossils. They're called zoophycos. These are crescent-shaped burrow patterns made by an organism mining for organic matter within the limestone. Underneath the limestone, there are black shales, probably carbon rich. They break into flaky pieces. It's very fissile. Don't worry about the yellow veins running through it. That's the weathering product of an iron-rich mineral, probably sulfur appearing on the surface. And then beneath the shale, something that breaks much more irregular fractures. Look at that shiny surface. This is a thin coal seam, and it rests on a sandstone. Well, the obvious way to summarise all those observations we've just been making on the limestone is to write a series of notes, and that's what I've done here. But there's another way of doing it that is more graphic, and that's to actually draw a profile through the limestone. So to do that, I've got a standardized graphic logging sheet. Vertically, there is a vertical scale, and we can select which one we want to use. In this case, we'll have each of these larger ticks representing 1 meter. And on the horizontal scale, we'll be able to represent the grain size of the sediment. So this is already labelled up, clay. We could draw a line up to here and it would represent clay, and then silt, and then fine, medium, and coarse sand. So let's make a start and put the limestone on that we've just been looking at. Well, I'll arbitrarily start it here. There's the base. As far as representing the grain size of limestones is concerned, if they were just composed of mud, we'd just draw the line across to the clay grain size, but because they contain a fair amount of skeletal material, we'll take it across to the silt. And then it's 65 centimeters thick, so that's how we draw it in. And the standard lithological symbol for limestones is a brick symbol. And it had a sharp base and a top, and the fossils we had in it where we had lots of crinoids, and that is a rather poorly drawn polygon, and putting a line through it represents skeletal material that's been broken up, in this case crinoids broken up. And the usual symbol for corals, which we saw there was one layer of corals, is showing colonial corals like that. Then right at the top of the limestone, remember, we had zoophycos. So I'll just represent that as this spiral pattern like that. And the final thing to note is that we had a fair amount of bioturbation. And this sort of stretched out S symbol is the usual one we use there. Well, remember, underneath the limestone, we saw some other rock types. There was about 30 centimeters of shale, so that's only clay grain size, and that's our symbol for shale. And then beneath that, about 15 centimeters of coal. That's very fine grain too. Shade that in black. And then underneath that, I didn't look at it in any detail, but there was a sand which was certainly medium grain sand, so we can extend it out to there and stipple it in, which is the conventional symbol for a sandstone. But what can we say so far about process as far as the limestone is concerned? Well, the lithology was entirely calcium carbonate, so that means there was no terrigenous material, no land-derived sediment being washed into the sea at that time. It was also entirely bioturbated, so no evidence preserved anyway of current action. So we may well have been below the influence of waves. And because it's calcium carbonate, we can postulate that it was a warm sea, and that's confirmed really by the presence of crinoids and particularly the corals. So the kind of process we have is precipitation of calcium carbonate in warm seas and beyond the limit of wave action. So it must have been relatively deep water. Now, above the limestone, there are certainly shales. We need to actually look at those. Here I'm at the top of the shales where they change quite abruptly into sandstones, and we'll look at those in more detail in a minute. But if we measure the thickness of the shales perpendicular to the dip of the limestone and the shales themselves, there's 5 meters here. So we need to look at them in a little bit more detail. And the first thing that stands out are these lines of orange-coloured nodules. Well, these nodules are lined up to the bedding, the laminations in the sediment. They show this bright orange colour because they're oxidising. They're probably formed of iron carbonate that's oxidising to iron oxide. And they're part of the burial history of the sediment. They formed as diagenetic products soon after the sediment was buried, perhaps only a few meters down, but they're not part of the depositional story. But something that very definitely is part of the depositional story is the very fine lamination we can see between some of these ironstone nodules, not disturbed by any burrowing. So it suggests a fairly tranquil environment with deposition dominantly from suspension. As well as the nodules, there's one other lithology present in these shales. In places, there are light-coloured streaks, for instance here and here, and many more of them. Now, are they present all the way through the shale? No, they're not. There are none towards the base, but the frequency of these lighter coloured intervals increases up the shale. So here's a couple of those lighter coloured layers. They're composed of silt and fine sand, sandwiched in between the shales. And they contain laminae, in this case parallel laminae, but in the lower one there are cross laminae, produced by the migration of ripples. Well, let's put these observations onto our graphic log. The shales are capped by sandstones, and they're showing some rather unusual features. Here's the contact between the shale and the sandstone. It's very sharp, very abrupt, but there's no clear cross-stratification. But what there is present are these pillow-like structures on the left here, and then to the right there are a couple that have been sliced through, and you can see that they're concentrically laminated, and the laminae curve up on either side, and then they're abruptly truncated. Where the truncation occurs, there must have been very rapid erosion. So what are these features? Well, they're called, not surprisingly, ball and pillow structures. And what must have happened is that these sands were deposited very rapidly on top of the shales. And both the shales and the sands would contain a lot of water. And as the sediment was compacted immediately after deposition, I mean, we're talking minutes perhaps at most, water would have been expelled from the system. And as it was expelled, it would distort the sediment into these pillow structures. And then later erosion would have planed them off. And we have probably maybe 1, 2, 3 events of rapid sand deposition, dewatering producing the pillows, and then erosion over the top. Although it's only the top one that shows the very clear erosional features. So these are rather unusual features, a combination of rapid sedimentation and deformation immediately after sedimentation. Now, above these ball and pillow structures are a number of sandstones. Here's the first one as a thin capping of shale, and then above it a sandstone showing low angle cross stratification. And there's a whole series: a thin shale, the sharp base sand, an irregular top to the sand, more shale, and another sand, and so on. And these contain some very interesting structures, low angle cross stratification, that we can see much better a little higher up the succession. Well, what's the shape of this bedding surface? There's a series of saucer-shaped depressions, and only occasionally are the little ridges between them gently convex up. Very often they're rather sharper than that. So in that case we've only got swales across most of this bedding surface, with just a few hummocks showing the gentle convex up morphology. And above this surface about 30, 40 centimetres above, there's a top of another bed, and that's showing some wave ripples on its upper surface. And in this direction, there's a wonderful slice through this bed again, so that we can see the internal cross-stratification structures. Immediately below the swaly surface, there's clear evidence of swaly cross-stratification, a series of low-angle troughs, but very little evidence of any hummocks. But in the next sandstone down, there's a very good example of hummocky cross-stratification, with the cross laminae inclined gently down to the left and arching up to the right. And then as we swing round and look at a cross-section almost at right angles to that one, there's a whole series of hummocks and swales visible. So basically, the geometry of these sandstones is broadly the same in whichever direction we look at them. And this is very characteristic of both hummocky and swaly cross-stratification. Now, all these sandstones are virtually devoid of fossils, but very occasionally we do see some trace fossils. These are called Diplocraterium, and we're looking down on them. You may find it hard to believe, but they are in fact vertical U-shaped burrows. But let's just look at the features in them first. Here's the best one. There's this sort of elongate, almost bone-shaped or dog bone-shaped feature, and you can just pick out some concentric laminae curving inwards at either end. Well, we're looking at these burrows in plan view. So what I want to do, using little sketches, is now explain how these burrow systems worked. Well, the best one we saw looked like this, with a little bulbous end, and another one there. And there were very faint concentric laminae at either end. And what, in effect, we're looking at is we're looking down on a U-shaped system, a vertical U-shaped system. So the burrows would have looked like this. And there would have been little shrimp-like organisms in here, perhaps several of them, and they're able to excavate sediment from the bottom of the burrow and plaster it on the top if they want to move down, or the other way around if they want to move up. So as the system moves, if it moved down, it would leave concentric traces. So that's going down. And likewise, if it moved up, it would leave these concentric patterns like that. And what we're seeing at this outcrop is a section through here. So we're not actually cutting through the U-burrow, we're just cutting through the concentric traces that it left behind. So it was clearly escaping, it was moving upwards as sediment was piled rapidly on top of it. So this is a very good example of an escape burrow system responding to very rapid sedimentation, just the sort of thing that we'd get as hummocky cross-stratification was produced. Well, here are the last of these two hummocky and swaly cross-stratified sandstones. We can see the hummock beautifully arching above the ruler there, but the sandstones above show a different geometry. They're sheet-like, with flat bases and flat tops, and they show parallel laminae instead of hummocks or swales. So here we've got sheets of sand and they're showing parallel laminae, and we can follow them down dip. And on some of these flat laminar surfaces, we can see wonderful primary current lineation exposed in fallen blocks on the foreshore. And we can also see some other structures present if we follow this bed down towards the sea. Right, well down here we can see some evidence. We've still got some hummocks, rather smaller this time, but above them there are some planar laminated sandstones, and they're a thin sheet, a couple of centimetres thick. And above that, some wave ripple cross stratification. You can clearly see the wave ripple morphology there. Pretty symmetric looking structures. Then some more parallel laminated sands. Then another wave rippled interval. And that's capped by a thin sheet of sandstone with parallel laminae. And we can see the top surface of that extending way along the cliff over there. And to see the top of this series of sandstones, I need to walk further along the cliff. Well, this surface here is probably about 20 centimetres above the big, extensive, flat dipping surface we saw before. And look at the shapes here. Each of these ridges is a symmetric ripple, but they're not lined up parallel. The orientation of the ripple crests is all over the place. So what we have here is a set of interference ripples. So this means the current in one time might have been oscillating like that, and then it might have moved like this. So it's very variable. But just underneath this bed, there is some more planar laminated sandstone. And this time, we can see primary current lineation in place in that direction. So here, we know that the current was either flowing away from me or towards me, which is in total contrast to what we're seeing here, where we had very variable oscillatory currents. Now there's one other feature we can look at here. Some high angle cross stratification. Remember, the tectonic dip is away from me in that direction at about 45 degrees. So this dip is at right angles to that. This is a sedimentary dip produced by the migration of quite a large scale bed form. This is a complete contrast to the wave ripples we've just been seeing. So we've an assemblage of three types of sedimentary structure. We've got planar laminated sandstones, wave ripple sandstones, and high angle cross stratification. And over here we can see the top of this sand unit. Now here there's something completely different. We've got this undulatory surface, and above it these black shales. And what are these structures here? Well, this is a familiar shape. We've seen this before lower down the sequence. And there's another one over here. These are diplocraterian burrows, the vertical U-shaped burrows. And they've carried the shale down into the sandstone. And I can also see another burrow type down here. We can see curved sort of crescent-shaped marks, and there's a suggestion, it's not very clear, that there may be a tube running alongside it there and another one there. So this could be a horizontal U-shaped burrow mining along roughly parallel to the bedding. If it is, this one is called rhizocorallium. Anyway, the whole of this little bed, about 10 centimetres thick, has been heavily bioturbated, and it's lost its sedimentary structures. And it indicates that sedimentation rates at the boundary between the sandstone and the shale must have been extremely slow in order to give time for the burrows to churn their way through the sediment. So now we're at the top of this sandstone unit, junction between the sandstone and the shale. It's time to complete the log again. Let's look now at the succession above the burrowed horizon. As we've seen already, the shale's immediately above that horizon, but within the shales there's some lighter bands, silts and sands, and we'll come back and look at those in a bit more detail in a moment. Look at the colour change. It's getting lighter upwards. Why should that be? Well, there's more sand and silt as we come in this direction, so this must be a coarsening upwards succession. And it's capped here by some quite well cemented sands, in contrast to the rather fissile shales and silts beneath. And then above this thin sand unit, there's some more shales and silts, But they then become rather more massive. We no longer see the fine laminae within them. And here, there's some black sediment. Well, we've heard that sort of sound before and seen this rather shiny material before. This is a coal. Look underneath the coal here. There's a root projecting diagonally down to the left. But just above it, quite thin, there's that softer sound that we get when we hammer shale. So we've got a coal seam, a thin shale, and then a limestone. So there are one or two things I want to show you in more detail about the sequence back down here. As well as the fine alternation of sand and shale, in the sands we can see that there is some mottling. I'm afraid the burrows in this case aren't very clear, but this mottle feature of these finely laminated sands is clear indication that there has been some burrowing, not enough to destroy the sedimentary lamination, but enough to disrupt it in places. And you can see this in several places as we go up. In fact, I think pretty well every one of these silt and sand layers has some burrows within it. But we can't see all the sedimentary structures clearly exposed here. So what I want to do is to show you a couple of features that are well exposed nearby here. This wave-polished surface shows beautifully the fine laminae in this part of the succession. Down here in the more shaly part, there's extremely fine laminae. So this must have been a very calm environment, not even disrupted by burrowing. And also in the sandier parts we get very fine laminae as well. So there's an alternation of fine, coarse, and in a couple of places, here and here, there is some disruption by burrowing. Well, here's a very thin sheet of sand, a couple of millimetres thick, running along there. But look above it. There's a little lens of sand here, another one there, and another one there. And these are probably tiny little wave ripples, and they're draped by the finer mud rocks. So that suggests deposition from suspension when the mud rocks were laid down, but some sort of traction current, probably wave currents, depositing the fine sand of the ripples. Well, let's complete the last bit of the log right up to the second limestone. Well, now we've finished the log and you've had a chance to think about the different processes that must have been operating up through this succession as it was deposited, we need to go over some of these ideas. And what I've done is spend about an hour drawing up a slightly neater version of the one that I put together whilst we were recording in the field, and here it is. Basically it's the same, the thicknesses are the same and so on, but I've had more time to put in all the lithological symbols and so on. So let's just remind ourselves of the succession of rock types we had through the succession. We started with a limestone, so there's one unit there. We then had 5 metres of shale. Then there was the ball and pillow horizon. And above that, the sandstones continued, but not with any of this soft sediment deformation, but with the hummocky cross-stratified sandstones. So that extended 7 metres up to there. Then the parallel laminated and wave ripple sands with the burrowed top. And then this coarsening upwards unit, and then another little coarsening upwards unit on top of that, showing the alternation of silts and shales and silts and sands. And then the coal with the root bed underneath, perhaps just add another root there. And the top part of this wasn't laminated like the bottom part, but was rather massive. And then there was a thin shale and then a limestone. Now in terms of process, back down to the bottom again, the limestone, remember, was deposited at a time when there was very little input of sediment from the land. If there'd been more sediment input from the land, we wouldn't have got a pure limestone. We also saw biotubation, we saw crinoids, we saw corals, clearly a marine environment. There were no well-preserved cross-bedding of any kind. the diatomation had probably destroyed it. But also, it was probably well below wave base, so it was only seldom reworked by exceptional storms. So the limestone represents the deepest part of the succession. But right up at the top, the coal and the underlying root bed are virtually terrestrial. The root bed is a soil, so it was probably just above sea level. And the coal would have accumulated in a swamp. So we're at sea level here, and we're down below wave base here. So it's clear that this succession from the limestone to the coal is a shallowing up succession. Relative sea level got shallower as we go up in this direction. Now, of course, we can explain changing sea level in a variety of ways. Maybe the shallowing is due to sediment actually filling a hole, and that's probably an important part of the story. But there may have been global sea level changes as well. So I've already summarized why we think the limestone represents the deepest part of the succession. But the shales too, they must be pretty deep, mustn't they? What's the evidence for that? Well, they're finely laminated, virtually no evidence of traction currents of any kind, except where we get these thin silt intervals. And remember, some of those contain cross-bedding, possibly even some wave ripples. So again, storms may have reached the sea bottom at this time when they were exceptionally strong. But the big change comes at the base of the sandstone, when, remember, these ball and pillow structures represent very rapid influxes of sand, presumably by storm processes, because we've got evidence of storm processes up here. And as the sediment, both the shale and the sand, dewatered, water expelled from the sediments actually produced the deformation that we see at this interval. Then we had an alternation of sharp-based sandstones and shales up the succession, the sandstones becoming dominant towards the top. And we saw abundant evidence of hummocky and swaley cross-stratification, which represents wave reworking, probably near storm wave base here and getting up to fair weather wave base up here. Then in this little unit, we have parallel laminated sandstones, wave rippling, and even one example of high-angle cross-stratification. So this is probably the only representative we have of the foreshore environment. And underneath, we're out in outer shelf here, and this would be the offshore transition. This part of the succession, this coarsening up unit in particular, I find a bit problematic to interpret. Normally one would expect to see more of these foreshore sediments and getting up into beach and even, maybe dunes, but we don't actually see that here. But remember what we saw: parallel laminae, wave ripples, a rapid alternation of shale and silt, which indicates deposition from suspension at one moment, deposition from traction currents at another. This has a feel of a tidal environment, but we didn't see other signatures of tides like herringbone cross-stratification. But in sediments lower down in this succession, we do have clear evidence of tides. So these might be possibly tidal flats, or maybe a lagoon actually behind an offshore sandbar. But when we're up here into the rootlet bed and the coal, we're on safe ground in terms of thinking in environment. Soil processes, waterlogged conditions that enable the vegetation to be preserved and not oxidized indicate soil overlain by swamp. And then above, we're back into shales. Here we didn't see any fossils, but in other instances of shale overlying coal in a succession just underneath the one we've studied, I've seen productus, brachiopods, almost sitting on the coal. So the deepening was very rapid, if that's the case. And then we're back to another limestone. So, what sort of environment was this? Remember at the beginning I said that if we could stack up our story of how processes change through time, in other words, up the succession, then we might be able to use that to say something about environment, and that's applying Walther's law. And that basically says if you see any succession of rock types vertically, that vertical succession would have existed in plan view at the time the sediments were deposited. So if we turn this on its side and imagine sort of walking across a margin of a subsiding area, we might have been able to walk, or swim rather, along the sea bottom and seen an area of limestone deposition. And as we worked up towards the shallower area, through the shales, through the storm rework sands, into the possible lagoon, up onto the swamps. So we can use this idea of Walther's law to get an idea of how these sediments stacked up. And I've drawn another little diagram I want to put beside this one. Well, what I've done now is to add along the side of the log a little sketch across the edge of a sedimentary basin. So land is over here. Here's the sea bottom, and here we're going out into deeper water. Here's the sea level, and here's roughly where storm wave base would be. So that's the maximum depth to which storm waves normally penetrate. So the idea of Walther's law is that if we see this vertical succession, then it should have been repeated as we swim shorewards. So out here is where the limestones would have formed. And then as we come shorewards, that's where the shales would have been deposited. And of course, as we come up, we're coming into storm wave base. So here, wave processes and storm processes would have driven sand, presumably from rivers somewhere, feeding sand into the sea, have been driven offshore by wave and probably tidal processes. And of course, reworked by wave action to produce the hummocky and swaly cross-stratification. And of course, as we came up the succession, we changed from the hummocky and swaly cross-stratification to planar laminated sandstones with primary current lineation, wave ripples, and even some high-angle cross-stratification. So we were probably just getting into the swash zone, into the foreshore here. And then, remember, this is the area I'm not too certain about. It might have been tidal flats or possibly a lagoon. So maybe there might have been actually a little depression there in which these sediments formed. And then finally up here, a swamp in which the coal formed, and of course the soil processes underneath. Now, to produce the vertical section, what probably happened through time, of course the sediments would build out. So each of these lines I'm drawing in are timelines, but they are also successive positions of the sea floor as the whole system built out. And so the sands would build out over the shales, and of course the limestones likewise would migrate in this direction. So this is the way we actually build up a vertical sequence of rocks from a prograding sedimentary system. In this case, probably a wave-dominated shoreline. What we've done, we've started by looking at evidence in the field, producing a graphic log, and as we did so, as we looked at each unit in this graphic log, we thought about the processes that would have laid down these sediments. And now, having got a whole succession of little process interpretations, we've been able to integrate these to produce a simple model to explain how this succession, sandwiched between two limestones, was laid down.